All right, hello everyone. I'm gonna go ahead and show you a simple model of a short polypeptide made up of 3 amino acids. I chose to link glycine, lysine, and alanine. And throughout this, I'll point out key structural features, including the amine groups, the carboxyl groups, R groups, peptide bonds, and the phi and psi angles, and then relate this to the secondary structures like alpha helices and beta strands. This is my model. I've gone ahead and just drawn a model using my note-taking app. And let's see here. And I have gone ahead and this right here is going to be glycine. This here is lysine. And then over here we have alanine. And then we can go ahead and point out some of the amine groups. Those are going to be the blue characteristic to the nitrogen groups. Right there, right there. And some of these groups are a part of the peptide backbone. These are found at the beginning of glycine within each of the peptide bonds. Peptide bonds are just bonds that kind of link the carboxyl group from the past amino acid to the amine group of the new one. And there, I chose to show them in purple. Each amino acid also has a carboxyl group. Those are going to be the oxygen double bonded to the carbon, as shown here, here, and here. Okay. And then I've also got the R groups that kind of help define each amino acid. So right here we've got the glycine, here of lysine, and here of alanine. And these R groups extend out from the backbone. Glycine has a tiny R group, just a hydrogen, and lysine has a positively charged side chain. And alanine has just a methyl group. These affect the folding of the polypeptide. So when it comes to peptide bonds, these connect each amino acid. They form between the carboxyl group of one amino acid and the amine group of the next. This linkage is rigid due to partial double bond character. When it comes to the phi and psi angles, each amino acid also has these rotational angles. Phi, as we can see here, is the angle around the nitrogen and alpha carbon bond, and psi is the angle around the alpha carbon and carbon bond. These determine how the polypeptide folds into secondary structures. So now we can go ahead and talk about those secondary structures a little bit more. So if the phi and psi angles allow, this polypeptide could adopt an alpha helix. Lysine and alanine favor helix formation, but glycine is very flexible, which may disrupt that. And as far as beta strands go, if the backbone extends, the peptide can participate in beta strand formation, where hydrogen bonds form between strands. And for turns, which is the third kind of aspect of developing the secondary structure, glycine is often found in turns because it's small and flexible, allowing the chain to bend sharply. So depending on the context, Gly-Lys-Ala could be part of an alpha helix, beta sheet, or a loop. So yeah, that's it for my polypeptide model. Just covered briefly the amine and carboxyl groups, R groups, peptide bonds, and the phi and psi angles, and how they influence secondary structure formation. I hope this made sense and that it was interesting to watch. All right, thank you.